Hello everyone. Now we are going to discuss about data science and semester paper. My name is Naveen Vashisht and my roll number is 34. So here we go. Question number 1. Distinguish between hypothesis driven and data driven paradigm in data science. Provide an example of each. Hypothesis driven and data driven. Hypothesis driven starting point begins from a predefined theory, assumption, or research question. Data driven begins from available data without a strong prior theory. Main goal of hypothesis driven is test whether a specific hypothesis is true or false. Data driven is to discover pattern, correlations, or structures in data. Approach of hypothesis driven is deductive, moves from theory to data collection, and approach of data driven is inductive, moves from data exploration to forming new hypotheses. Data collection of hypothesis. Data is collected in controlled way to answer a precise question, and approach of data collection for data driven is uses large often existing data sets. Collection may be broad and open. Typical technique: statistical technique, controlled experiments, A/B testings are used in hypothesis. Data driven: data mining, machine learning, clustering, predictive modeling. Role of domain knowledge in hypothesis driven is very strong. Domain expert defines hypothesis and variables. In data driven, important but sometimes secondary to algorithm discoveries. Flexibility of hypothesis driven is like it is less flexible, limited to the hypothesis, but in data driven it is more flexible, can reveal unexpected patterns and new questions. Structured versus unstructured. In a structured organization, highly organized in predefined rows, columns, and data types. Unstructured, no fixed schema, information is free form or loosely organized. Storage format, relational database, spreadsheets, CSV tables, and text documents in unstructured, images, audio, video, social media platforms. Ease of querying. In structured data, easy to query using SQL or similar query languages. In ease of querying in unstructured data is difficult to query directly, often needs pre-processing and algorithms. Typical analysis of structured data is descriptive statistics, dashboards, traditional BIML models. In unstructured, text mining, NLP, image processing, speech recognition, deep learning. Example of structured data is bank transaction table, student marks table, sensor log. Example of unstructured data is email, customer reviews, photos from CCTV, record phone calls, and etc. Structured data follows a strict schema such as table with columns. These are all the explanation of above points we did. Quantitative versus categorical data. So numerical values that represent counts or measurements are in quantitative data. Non-numerical labels categories describes are in categorical data. Used for arithmetic operations like addition, mean, variance are the main purpose of quantitative. Used for grouping, classification, and frequency counts are of categorical. Subtypes of quantitative are discrete and continuous. Subtype of categorical are nominal and ordinal. Allowed operations can compute some averages, standard deviation, correlation. Categorical can compute mode, proportion, core, cross tabs, numeric cross. And examples of quantitative are height in centimeter, weight in kilogram, categorical, gender, blood group, product category, etc. So this is the explanation of above all these points that I explained to you. Write an algorithm that uses Bayes theorem for decision making. Write an suitable algorithm, that is part B. So we are looking for part A now. Bayes theorem. Identify all possible cases C1 till Ck and the relevant attributes of the instance X. From training data, estimate the prior probability of each P of Ci and the conditional probability of each attribute value given a class P of X, J, Y, Ci. For the new instance, capital X is equals to x1 till x and compute the posterior probability of every class using P of Ci by x proportional P of Ci. Summation j is equals to I to n P of xi by Ci. Now normalize the posteriors if required so that the probability is sum 1 across to the classes. Fifth step, select the decision or classes labels with maximum posterior probability. Decision is equals to argument of max of probability of Ci by capital X. Output. The chosen class for the instance X and if needed its probability as confidence. This algorithm is commonly used in classification problems such as email spam detection or medical diagnosis. Algorithm. Question number 2 to the part B. Algorithm for association rule mining that prints all association rule. You can write a priori algorithm steps followed by rule generation from frequent item sets. Part A priori to find frequent item sets. Input transaction database D, comma minimum support threshold minimum underscore support. Generate the set of candidate one item set C1 by listing all the individual items in the database. Scan the database to count support of each candidate in C1. Keep only those values support greater than equals to minimum of support to form frequent one item set L1. For k is equals to 2, 3, generate candidate k item set ck by cell joining lk to the minus 1 and removing those whose any k of minus 1 is subset and not frequent. Scan database to count support for each candidate in ck. From lk, but keeping candidates with support greater than equal to minimum support, stop when lk becomes empty. Part 2. Generating and printing all association rule. First, input all frequent items as L and minimum confidence, minimum of confidence. Second, for each frequent item set F in L with F greater than equals to 2, generate all non-empty proper subsets A to F. For each subset A, let B is equals to F slash A. Compute confidence of rule A implies B as confidence of A implies B is equals to support of F by support of A. If confidence is greater than equal to minimum underscore confidence, print the rule A implies B with its support and confidence. After processing all frequent item sets, all high confidence association rules are printed. This procedure mines items so occurrence patterns and report all valid association rules that satisfy the given support and confidence thresholds. Question number 3. Part A. Compute mean, median, mode, and standard deviation for a given small data set. Example when each measure is appropriate. Mean. Formula for n values x1, x2 till xn is mean is equals to summation of xi divided by n. For the data set, we have 40, 50, 50, 60, 90, then we will add this and divide it by 5. So this is 290 by 5, which will be given 58. When appropriate, best for symmetric numeric data without extreme outliers used in many statistical procedures and for overall performance like average marks or average items. Median, which is the middle value. Arrange data in ascending order 40, 50, 50, 60, 90. For odd and median is middle value. So the here median is 50. When appropriate, preferred when data is skewed or contains outliers. Given a better central value when one or two extreme values would distort the mean. Mode. The value occurring with the highest frequency is the mode. In the dataset, 50 appears twice, the other appears once, so mode is 50. When appropriate, use for categorical or discrete data such as most common blood groups. Favorite for product, most frequent grade. Standard deviation. Spread out of data. Find deviation from mean. 40 minus 58 is minus 18, 50 minus 58 is minus 8. We will go on like this and square the deviation. We will give square of all these, like 8 to the square is 64 and all we are writing here. Now variance for, we will add these and divide by 5, which will give us 296. So now rooting this will give us standard deviation. Variance is root of standard deviation. Okay, standard deviation is root of variance. When appropriate, indicate how tightly data points cluster around the mean. Small values means low variability. Used in risk analysis, quality control, comparing consistency of performances. For example, two students with the same mean marks but different spread. Errors in data and artifacts. Errors are incorrect values that do not represent reality. Artifacts are unwanted pattern or distortions introduced by collection or processing. Error are typing mistakes, wrong units, misrecorded measurements. Artifacts is sensor malfunction, system glitches, pre-processing bugs. Errors are age recorded as 250, negative salary date, like this. Sudden spikes in ECG signal, duplicated record after import. Errors are error on impact analysis, leads to wrong statistics, wrong models, misleading conclusions, correlates artificial trends or correlations that are not truly present. Treatment and cleaning, correct or remove incorrect values after verification, detect source of artifacts and filter smooth or removed. Any two imputation technique, mean median imputation. Replace missing numerical values by the mean or median of that attribute computed from non-missing records. Mean is suitable for roughly symmetric data. Median is better when data is skewed or has outliers. Simple to implement and quick for small to medium data sets, but it can reduce natural variation because many records share the same imputed value. K nearest neighbor imputation. For a record with missing values, find K most similar records based on other attributes. For a numerical attribute, impute the missing value as the average of the attribute in the k neighbors. For categorical use, the most frequent category among neighbors. This method preserves local structures of data and gives more realistic values than simple mean, but it is computationally more expensive and sensitive to the choice of distance metrics and question number 4. Explain any 4 common feature engineering techniques for continuous or categorical data. Scaling and normalization. Rescales numeric feature so they are on similar range. Example, standardization, mean divide by standard deviation or min-max scaling too. Helps gradient based models, logistic regression, neural network, coverage faster and prevent features with large units from dominating distance. Based model like scan and k-means. Binning converts a container variables into intervals or bins such as turning age into groups, reduces noise and make patterns easier to interpret and is often used in decision trees or risk scoring rules where ranges are more meaningful than exact numerical values. One hot encoding transforms a categorical feature with k possible values into k binary columns, each indicating presence 1 or absence 0 of one category. Interaction and polynomial features. It creates a new feature by combining existing ones. For example, product of two variables, area is equals to length into breadth. Capture non-linear relationships and interactions between variables that a simple linear model cannot express, improving predictive power when chosen carefully. Question number 4b. Sampling from distributions and inverse transformation sampling. What is sampling from a distribution? What is? Okay. Sampling from a distribution means generating random values such that their long-run frequencies follow a specialized probability distributions. Example, normal exponential Bernoulli. In data science and stats, this is used for simulation, Monte Carlo methods, bootstrapping, and creating synthetic data sets when real data is limited or expensive to collect. Inverse transformation sampling generate samples from a continuous distribution with cumulative distributive functions. Steps: generate a random number u from a standard uniform distribution 0, 1. Compute x is equals to f inverse of mu, where f inverse is the inverse of CDF. The value x is a sample from the target distribution. Repeat step 1 to 2 to get more samples. Suppose the target is an exponential distribution with rate lambda. It's a CDF. F of x is equals to 1 minus e to the power minus of lambda x, where x is greater than equals to 0. To invert set u is equals to f of x equals to 1 minus e to the power minus lambda. Distinguish between parametric versus non-parametric models and supervised versus unsupervised learning. Parametric models, number of parameters are fixed independent of data sizes. Non-parametric grows with data, complexity increases with more samples. Aspect, assumption on form. Assume a specific functional form, non-parametric form. Make fewer assumptions about underlying function distribution. Data required in parametric is work well with smaller data set. In data required in non-parametric, usually need more data to generalize well. In parametric, training speed typically faster with smaller, simpler optimization. In non-parametric, often slower with memory intensive. Example, linear regression, logistic regression, native bias, and in non-parametric KNN, decision tree, random forest, kernel SVM. Here explanation of that what I just explained you. Supervised learning versus unsupervised learning. In supervised learning, availability of labels used as labeled data. Each input has a known target output. In unsupervised learning, uses labeled data, only inputs, no target output. Goal is learn mapping from inputs to output for prediction. Unsupervised learning, discover hidden structure, groups or pattern. Typical tasks: supervised learning, classification, regression; unsupervised learning, clustering, dimensionality, reduction, association mining. In evaluation, supervised learning, usually using metrics like accuracy, RMSE, precision, recall; and unsupervised learning using measures like clusters, cohesion, Sehauge, variance explained. Example, spam versus not spam. So email classification, house prediction. In unsupervised learning, customer segmentation with k-means PCA for feature reduction. Here is the explanation, what I explained just to you. Now B part, accuracy, precision, recall, F1 score using a confusion matrix. TP is true positive, TN is true negative, FP is false positive, and FN is false negative. So the accuracy formula is this: TP plus TN by TP, TN, FP, FN. So precision is TP by TP plus FP. The recall sensitivity or true positive rate is TP by TP plus FN. F1 score is 2 times of precision into recall by precision plus recall. Describe how the coefficients in linear regression are estimated using either the closest form or equation or gradient descent. Sixth B. Explain logistic regression and other. So starting with answer A. Estimating coefficients in linear regression, consider multiple linear regression. Y is equals to x of w plus epsilon, where x is the matrix of input, w is the vector of coefficients, y is the vector of target values. Closed form normal equation. Define laws as sum of squared errors. J of w is equals to 1 by 2m of xw minus y to the whole square. Differentiate J of w with respect to w and set derivatives to 0. The solution is w is equals to x transpose x to the power whole inverse x transpose y. Provided xtx is invertible, the directly gives the coefficient vector that minimizes squared error. It is accurate but can be expensive when numbers of features is very large or matrix is nearly singular. Gradient descent method. Start with initial guess W0. For example, all zeros repeat until convergence W to the power t plus 1 is equals to WT minus alpha delta JWT. And similarly, this is the formula or other we can see here. So now stop when change in W or in cost J of W becomes very small or after fixed number of iterations. Gradient descent is suitable for large data sets and online learning because it does not require matrix inversion and can be implemented as batch, mini batch, or stochastic gradient descent. Logistic regression and probability for a class. Sixth part of B. Okay. Logistic regression is a supervised learning algorithm used for binary classification where the target value y takes value 0 or 1 instead of modeling y directly as a linear function of inputs. It models the probability that y is equals to 1 given input vector x using the logistic sigmoid function. Model and logistic function. Compute linear combination. Z is equals to w to the power t of x plus b, where W is coefficient vector and B is bias intercept. Power pass Z through logistic sigmoid function. Sigma of Z is equal to 1 upon 1 plus e to the power minus of x. Decision rule. Predict class 1 if P of y is equals to 1 or by x greater than equals to 0.5 or another threshold other predict 0. Example of probability calculation. Assume a simple model with two feature x is equals to x1, x2 and learned parameter w1.8, w2 minus 0.4, b 2.2, x1 is 2 and x2 is 1. Compute z. So applying formula we will get z as 1 and compute probability of class 1. P of y is equals to 1 by x. We will get sigma as 0.373. Thus the model estimates a 73% probability that the instance belongs to class 1 with a 0.5 threshold. Class 1 would be predicted. Write a k-means clustering algorithm. Discuss how initial centroids influence the result. Write k nearest neighbor algorithm. So algorithm steps for k clusters. Choose the number of k, initialize k centroids, usually by picking k data points at random. Assign step for each data point, compute distance to every centroid, and assign the point to the nearest centroid cluster. Update step. After all points are assigned, recompute each centroid as the mean of all points currently in that cluster. Repeat step 2 or 3 until cluster assignments no longer change significantly or a maximum number of iterations is reached. Output final k clusters and their centroids. How initial centroid influence results. Different random initial centroids can lead to different final clusters because k means may converge to a local minimum of the objective function. Poor initial centroids may cause empty clusters, unbalanced clusters, size or centroids stuck in suboptimal location. To reduce the sensitivity, common practices are run k-means multiple times with different random starts and choose the best solution, or use smarter initialization method like k-means plus k nearest neighbor algorithm using Euclidean distance. Consider a dataset with labeled example xi, yi, where xi is the feature vector and y is a class label. Choose k the number of neighbors for a new unlabeled print x. Compute the Euclidean distance from x to every training point xi. D of x comma xi is equals to under root of summation j is equals to 1 to n of xj minus xji to the power whole square, where n is the number of features. Sort all training point by increasing distance to x. Select the k closest neighbors. For classification, count how many of these k neighbors belong to each class and assign to x the class with highest count. For regression, take the average of the target value of the k neighbors as the prediction. Question number 8 to the power 8 to part A. Compare decision trees, random forest, boosting, highlighting strength and weakness of each. Decision tree, random forest and boosting. Idea decision tree splits data using feature test. Random forest many built trees or random samples and features than average. Boosting means sequentially builds weak learners where each correct previous. In decision trees, low bias, high variance, but in random forest, lower variance than a single tree. Boosting very low bias can have higher variance if overfitted. Overfitting decision trees prone to overfitting without pruning. Random forest overfitting, less overfitting due to averaging of many trees. Boosting can overfit it too many iterations. Interpretability in decision tree is higher interpretable, but random forest is less interpretable, where boosting is also less interpretable. Training time to train decision tree is very fast to train for modern feature size, but random forest is slower than one tree but parallel as well. Boosting users slower trees built sequentially. Performance decision trees performance is moderate accuracy, but random forest generally higher accuracy and robust, whereas boosting often highest accuracy in complex problems. Use case quick baseline model gives a simple rule extraction and decision trees. Tabular data where data accuracy and robustness are important. Computation high accuracy applications like credit scoring. Question number 8 of part B. Hadoop architecture and component HDFS, YARN, MapReduce. Whereas Hadoop is a framework for distributed storage and parallel processing of big data on clusters of commodity hardware. Its core modules are HDFS for storage, YARN for resource management, and MapReduce for processing. HDFS, Hadoop Distributed File System. It stores very large files by splitting them into fixed blocks. For example, 128 MB and distributing these blocks across data nodes in the cluster. A name node keeps metadata while data nodes store actual data blocks and periodically sends heartbeats, replication of blocks, provide fault tolerance. YARN, yet another resource negotiator, act as a cluster resource manager and job scheduler, decoupling resource management from application logic. The resource manager assigns container on node managed over applications. On application master coordinates each application's task and monitor progress. Map reduce processing model. A job is expressed as map and reduce functions. The map storage process input key value pairs and emits intermediate key value pairs. The framework groups them by a key and passes them to reducers. The reduce stage aggregates value by key to produce final outputs, which are written back to HDFS. Its model automatically handle data. Spark and its advantage over MapReduce. Apache Spark is a distributed computed engine that keeps data in memory between operation using resilient distributed data bit or data frames. Key advantage over classical MapReduce. Supports in-memory computation, so iterative algorithm and interactive queries run much faster than disk-based MapReduce, which writes intermediate results to HDFS after every step. Provides rich high-level APIs in Scala, Python, Java, and SQL along with libraries for machine learning, streaming, graph processing, and structured processing. Offer flexible execution beyond map and reduce, including joins, filters, window operations, and complex DAG workflows, improving expressiveness and performance for many data processing tasks. Question number 9. Obtain basic logic gates from neural networks, summarize them in a table with the number of neurons, activations, functions, and backpropagation in neural network. Logic gate. AND or NAND or one neuron in each, where W1 is 1, W2 is 1, B is minus 1.5. Step is binary, activation function step binary. Output 1 only when both inputs are 1. Similar in or output is 1 when at least one input is 1, and in NAND opposite of AND gates, and in NOR opposite of NOR gates. Any scaled weight and biases giving the same decision boundary are also valid. CNN, RNN, GAN, transfer learning. Core architecture of CNN is convolutional plus two-ring layers followed by dense layer. In RNN, recurrent connections, hidden state carries information in time. GAN, two-net generator and discriminator trained in a position. Transfer learning, reuse of a pre-trained network on a new related task. Data type handled. grid-like data, images, video, frames, spectrogram, RNN, sequential data, text, speech time series, GAN, any data type where generator and discriminator can be defined, transfer learning, any domain where similar pre-trained model exists. Main purpose of CNN is feature extraction and classification of spatial patterns. Main purpose of RNN is modeling temporal dependencies and sequence. Main function of GAN is generating new realistic samples resembling training data. Main purpose of transfer learning is improved performance and reduced training data needed. Training behavior, parallelizable large GPUs, commonly used. It's harder to train, and GANS training is unstable, needs balance between generator and discriminator. Transfer learning usually fine tunes only last layers, faster convergence. Typical application of CNN is image classification, object detection, segmentation, vision tasks, language modeling, machine translation, speech recognition, stock prediction. GAN is image synthesis, style transfer, data augmentation, and etc. CNN learn local spatial feature with shared weights, making them very effective and barren. RNN processes input sequentially, maintaining a hidden state quo so that each its output depends on previous element, useful for language and time series tasks. GN bet a generator against a discriminator. The generator tries to create fake but realistic samples, and the discriminator tries to distinguish real from fake, leading to powerful generative models. Transfer learning takes a model trained on large generic datasets and fine-tunes some layer on a small task-specific dataset, saving computation and improving performance when labeled data is limited. Thank you everyone for listening to me, and I hope you all got my topics explained by me.